All right, let's go on to the main content where we are dealing with regular calculus problems. And let's do an example, kind of like the example that we did at the end of class last time, where we just have a graph. And I'm going to make the graph fairly simple, piecewise linear, and try to think about how this graph can be used to define an antiderivative of itself. This graph is going to be a derivative of a function we're going to create from it by thinking about areas, ultimately signed areas, because they're going to let the graph go both above and below the axis. Okay, so this is going to be kind of tricky, but I think it's worthwhile. And this is something, especially if you take Calc 2, that I emphasize in that class as well, to really make sure you understand what's going on here. This is definitely a worthwhile thing to do. So we'll start with the graph. Let's say the graph starts out horizontal for a while, and then goes down along a straight line like this. And let's keep it just to that far. But we'll make it go down a little further here. I won't make it go like straight over here. I'll keep it like this with piecewise linear with two pieces. For the sake of concreteness, let's say this is the number 3 here. This is the number 5. And let's make this the number 8 on the horizontal axis. So it is going down below the axis there further than it is going down above the axis here. Yeah, I gotta make up something for the height. Let's keep it fairly simple. Let's make this 2. And if we're going to be consistent here, the slope of this part here is going to have to be rise over run would be -2 over 2 is -1. So if the run continues from 5 to 8 to be 3, I got to go down another 3 times down to -3. Yeah. The slope is -1. It's got to go down another 3 units as x increases by 3 units from 5 to 8. Okay. So this is a function. I'll go ahead and call this function f of x, little f of x. Let's be consistent here. Or maybe, okay, here we go with the lettering. Maybe I should, let's scratch that out. Let's call it f of u. And let's label this axis u. Why? Well, partially because I'm going to integrate this, and I'm going to have a variable in the upper limit of the integration that I'm going to want to call x. And so I'm trying to use some other letter for the variable on the axis. Does it matter to call it u? I mean, does that mean anything? No. I just want to use something different than x. I could use v, I could use w, I could use some other letter. Don't worry about the letter. I know that gets confusing, but that's not what to focus on. I do want to define a function now, a capital F function, capital F of x, to be an integral of little f of u. But I don't want to leave it like this because that looks like it's just a plain antiderivative, an indefinite integral. And if it's got a u there and a u there, you'd say the answer does involve u. I want this to be a definite integral where the variable is in the upper limit of the integral, x. And what should I put for the lower limit? I mean, the most natural thing to pick is 0. But on purpose, I'm going to pick something other than 0 to show you that I can if I want. How about I pick 2? That was arbitrary. I could have picked 1. I could have picked 3.4. There's infinitely many choices I could have had here. I decided to pick 2. Right about there. What I'd like to do is I'd like to find a formula for capital F Not by finding a formula for little f first, although, well, okay, I guess I lied a little bit there. It probably would be good to have a formula for little f. But what I'm trying to say is, I'm going to write down a formula for little f, but I want you to realize that in doing the integral to find capital F, I'm not going to think about integrating the formula for little f in the usual way. Instead, I'm going to think about areas. And what's the goal in all this? The goal is to illustrate the truth of what our book calls the second fundamental theorem of calculus in chapter 6. Other books call it the first fundamental theorem of calculus. I actually think the other book's idea is better to call it the first fundamental theorem of calculus, but I'm staying consistent with our book and calling it the second fundamental theorem of calculus, that this function right here is an antiderivative of little f. Its derivative, capital F prime of x, equals little f of x, if you want to go ahead and call the variable x. You want to be consistent. But if I'm calling the variable for little f u, as I am up here, what's the formula? Well, it's constant 2 if u is between 0 and 3. And it's the graph of that line, whatever its formula is, when u is bigger than 3, between 3 and 8. That's a line with a slope of -1. It's also got a u-intercept at 5. Actually, that can help me quickly find its formula. If you think about it carefully, its formula would be negative of u minus 5, which is the same as negative u plus 5. You don't have to think about the vertical intercept, though you could. It is consistent. If you go backwards here, you're going to go, if you let u decrease from 3 down to 0, since the slope is -1, this graph's going to go up by 3 units to 5. The vertical intercept is 5. But to come up with this formula, I just thought about the fact that the horizontal axis intercept is 5. That's why I have a u minus 5 in there. And then I also have a slope of -1, so I need a negative sign out in front. But yes, that does equal negative u plus 5. That'll be helpful, okay? But now we want to think about the formula for capital F, again, case by case. First case, case 1. Easiest case. Let's say x is between 2 and 3. Now I'm using strict inequalities here. I wouldn't really have to, especially in, well, in the case where x equals 3. The pictures I'm going to draw are going to be typically in the strict inequality case. If x is between 2 and 3, pretend it's right here. The integral, which gives you the formula for capital F, it is the formula for capital F. Since the graph of little f is above the horizontal axis, is the area of this rectangle right there. I'm thinking about finding this formula using geometry. That's why I'm using straight lines for the graph of little f, because if I use curves, then it gets, well, more complicated. I have to use antiderivatives to help me find areas in that case, and I'm trying to avoid that because I'm trying to ultimately show I do get an antiderivative by just thinking about these areas. That again is the goal. What's the area of that? It's base times height. Base is x minus 2. Height is 2. Capital F of x in this case, base times height is x minus 2 times 2, or 2 times x minus 2, 2x minus 4. And hey, yeah, that is a function whose derivative is always 2. The value of little f, when its input is between 2 and 3. So far, we are getting a function whose derivative is little f. Does that continue in the other cases? Next case. Case 2. X is between 3 and 5. Okay, and here it gets a little funny. I'm going to go ahead and write a strict inequality in both spots. Reason being is if x is between 3 and 5, your typical drawing might look like this. And I'm going to ultimately be thinking about an area of a rectangle and also the area of a trapezoid. And if x equals 5, it's really a triangle. The formula still works in the case where x is 5 ultimately, but just to avoid confusion. If x is between 3 and 5, then it's right there, say, somewhere between 3 and 5. The integral still is the formula for capital F. The graph of little f is still above the horizontal axis. So the value of little f is still an area. It's still this area of this rectangle plus this trapezoid. That rectangle is a fixed rectangle. If x is between 3 and 5, it's not changing, no matter what x is between 3 and 5. Its area is base times height. The base is 1 now. I'm shading the entire rectangle. The height is 2. 1 times 2. What's the area of a trapezoid? I've mentioned this. It's the base times the average of the heights. What's the base? Somebody tell me. What's the base of that trapezoid that I'm pointing at? X minus 3. Base times the average of the heights. One height is fixed, 2, right there. The other height depends on what x is. In fact, it's the value of little f at that value of x. Call it f of x, not f of u, because I'm thinking of x as being this fixed number. Base times the average of the heights. Add up the two heights, 2 plus little f of x, and divide by 2. Now simplify all this. 1 times 2 is 2. What's f of x? When x is between 3 and 5, it's this thing when you replace u with x. Go ahead and be careful here. I don't want to make a mistake. F of x is negative x plus 5. Right? I'm thinking of u as a variable in this formula, but here I'm thinking of x as fixed, although it could be anything between 3 and 5. Some fixed number between 3 and 5. The height of that line segment is the second coordinate of this point. It is the value of f of x. Replace u with x. Get negative x plus 5. Continue simplifying. Like that. Factor to 1/2 out. Continue simplifying. FOIL. Negative x squared. Outside times outside is 7x. Inside times inside is 3x. So it's plus 10x. Negative 3 times 7 is minus 21. Distribute the 1/2 through. In the end, I get negative 1/2 x squared. 1/2 times 10x is 5x. 1/2 times negative 21 is negative 21 halves, which is negative 10.5, plus 2 is plus 12.5. Already there's a decimal. Excuse me, minus. No, sorry. Minus 10.5 plus 2 is minus 8.5. Sorry. Huh, that's a weird formula. That's you could call it an unexpected formula. But guess what? Its derivative is negative x plus 5, right? Negative x plus 5, the same as little f when I replace u with x. That's good. That's an antiderivative. What about the minus 8.5? Where does that come from? Is that right? If I haven't made a mistake, it's right. Why is it minus 8.5 instead of something else? It will make capital F continuous, including at the boundary of these two cases at x equals 3. If you replace x with 3 right here, you get 2 times 3 is 6 minus 4 is 2. What if you replace x with 3 here? What do you get? 3 squared is 9 times negative a half is negative 4.5. Negative 4.5, 5 times 3 is 15. Negative 4.5 plus 15, positive 11.5. What, did I make a mistake? No, negative 4.5 plus 15 is 10.5, not 11.5. 10.5 minus 8.5 is 2. That's 2 when x is 3. This is 2 when x is 3. I'm piecing together not only an antiderivative, but it's also a continuous antiderivative. Better be differentiable as well. That's not so clear. Is it possible the graph is continuous at 3, but maybe it has a corner in it? We'll have to wait and see. Next case. I'm noticing my power going down. I thought it was plugged in here. Next case. Guess I'm going backwards here. Case 3. How about when x is between 5 and 8? How do you do that? The formula for capital F is still this integral. That never changes. The way you think about the integral in terms of areas is what changes. All right. Well, it's the integral from 2 to x, so it's still going to give me an area under the graph over here, including this little triangle that hasn't been shaded yet, but then minus this area. Because when the graph is below the axis, the area between the graph and the axis contributes to the integral negatively with the minus sign. This thing here is actually a sideways trapezoid with its base equal to the original height over here, 2. And what's the average of the heights, though those heights are sideways? This height is 1, this one is 3. 2 times 1 plus 3 over 2. Ultimately, the area of this is 4. I didn't have to think of it that way. I could think of it as this rectangle plus this triangle. This rectangle has area 2. This triangle has area 2 as well. 1/2 times base times height. 2 plus 2 is 4. Either way you think of it, the area of this is 4. This is a 4. But then I have to subtract the area of this triangle because it's below the axis. 1/2 base. Base is x minus 5, right? If I think of this as the base here on the top, maybe I shouldn't call it a base. Height is this. Now, the second coordinate of this point is little f of x. However, that point is below the axis. So technically speaking, as a height, that height is the opposite of little f of x. And the opposite of little f of x is a positive number when x is bigger than 5. 1/2 base times height. The height is the opposite of little f of x. But I am subtracting this positive quantity. So in the end, I'm subtracting, I'm making it smaller. Should I say that again? This is really key. This is the trickiest, well, one of the two trickiest parts. I got one more case after this. if x is less than 2. That contributes positively to the integral because the graph is above the axis over here. This area contributes negatively to the integral. I have to subtract a positive area. Or add a negative area if you want to think of it as a negative area. Either way is okay as long as you're consistent. Wait, negative area? Is that allowed? It's allowed if we say it. If you say areas below the axis are negative areas, then you've said it, and you can do that if you want. Then you'd be adding a negative area, but it's probably better to say subtracting a positive area. It's a triangle. Area is 1/2 base times height. Think of the base as the top, and its base is x minus 5, and that's a positive number when x is bigger than 5. Height is this distance here. It's not equal to f of x because f of x, when x is bigger than 5, is a negative number. Its height is the opposite of f of x. So I need a negative sign there. But this quantity right here, when x is bigger than 5, is positive. I am subtracting something positive. Now simplify. I'll go ahead and combine the negative signs to make a plus sign here. And just write f of x here. F of x, if I replace u with x, is negative x plus 5. Very easy to make a mistake. You got to be careful. FOIL again, get negative x squared. 5x plus 5x is 10x. This is feeling familiar somewhat. Negative 5 times 5 is minus 25. Kind of similar to what happened here. Is it going to end the same? (25/2) is 12.5. Negative 1/2 x squared plus 5x minus 8.5. How about that? Oh, why did it do that? That's astonishing. We got the same thing. Well, if math is consistent, we had to. Because I still need to get an antiderivative of little f, and it's still got to be a continuous function. It's got to be the same thing. It's the same line here. Isn't that cool? I think it's really cool. All right, final case. Case 4. X is between 0 and 2. And I guess I can include 0. Go back up to the picture. X over here, say. The formula for capital F is still the exact same formula as an integral. The integral from 2 to x of little f. But x is less than 2. Well, that's okay. We talked about what to do in that case. You just switch the limits around and negate the whole thing. Write it like this. That's what you do. That was a definition, right? Talked about that on Wednesday. If you switch the limits of integration around, which you can do if you want, just put a negative sign in front of the integral. Does that mean this is a negative quantity? Not necessarily, though maybe. Actually, it will be. This integral from x to 2 now, when x is less than 2, is a positive quantity. It's this area right here, which that's a rectangle. We're still with a height of 2, but now the base is 2 minus x. as a distance, right? If that's going to be positive, if x is 2, it's got to be 2 minus x, not x minus 2. The area of that rectangle is 2 times 2 minus x. But don't forget about your negative sign in front. Ultimately giving you 2x minus 4. And hey, that's the same thing we got for case 1, 2x minus 4. Yay. That's consistent with this. It had to be the same thing. How you get there is different when you're thinking about areas and signed areas and switching limits around and putting negative signs, but it's got to all be consistent if it's going to fit together. And yes, we have finally confirmed really what the final answer is for capital F. I mean, in all cases, well, okay, including the boundary case, it does work out when x equals 0 and when x equals 5 and 3. It all works out the same. You can write capital F of x is 2x minus 4 when x is between 0 and 3, and negative 1/2 x squared plus 5x minus 8.5 when x is between 3 and 5, or 3 and 8. And I'm including 3 in the first case and not the second. I could have done it the other way around because this is continuous at 3. I could have made that a strict less than and made this a less than or equal to. And what is the derivative of capital F? The derivative of the first piece is 2. The derivative of the second piece is negative 2x plus 5. What about the boundary? X equals 3 for these two cases. Can I write a less than or equal to here? Is this a continuous function at 3? If I put a less than or equal to there? Yes, it is. Because if you plug in 3 there, you get, did I make a mistake? Yeah, negative x, sorry. If I plug in 3 there, I get negative 3 plus 5, 2. It matches. So I can put a less than or equal to there, or there if I prefer. What does the graph of capital F look like? Well, this is the derivative, sorry. This, and it equals little f of x. And notice I'm putting a little x there instead of a u. That's what I should do if I want these variables to match, which I should want. If I'm calling this one x, I better call this one x. It doesn't matter what you call it. You could call it t if you wanted to. Z, V, W, treble clef. It doesn't matter. The variable name doesn't matter. It's just a symbol. That's all it is. We're so used to x that we can't think of anything else sometimes. What matters is the rule. You know, functions are defined by rules. This function in particular has an output of 2 whenever the input is between 0 and 3, and has an output of the negative to the input plus 5 whenever the input's between 3 and 8. What does the graph of capital F look like? I won't try to sketch it super great, but well, maybe I should be careful here. It's a line with a slope of 2 and a vertical intercept of negative 4 when x is between 0 and 3, which does mean it has a horizontal intercept at 2 and gets up to a value of 2 by the time you get to 3. This is the capital F graph that I'm making. Think about it. I'm looking at this formula in purple. Slope of 2, intercept of negative 4. When x is 2, this is 4 minus 4 is 0. When x is 3, it's 6 minus 4 is 2. It's got a slope of 2 everywhere. Its derivative is little f. It had to have a value of 0 when x is 2, because when x is 2, the integral is the integral from 2 to 2. No area. 0 is the area. By making that lower limit of the integral 2, I was guaranteed to get a capital F function whose graph has an x-intercept of 2. Guaranteed. Which I did. If I had made the lower limit something else, like 1.5, I would be guaranteed to get a capital F whose x-intercepts 1.5. But wait a minute, doesn't the answer have to be the same? No. If I put a different lower limit of the integral, I still get an antiderivative of little f, but it's a different antiderivative. It's a vertical shift of this one up by a certain amount. If x is 1.5, it would go up by a certain amount. Up by 1 unit, I think. Is this making sense? Can I clarify anything? It's weird. This problem's weird, right? Long and weird. But it's super important, I think, if you're going to believe the second fundamental theorem of calculus, which you should want coming out of Calc 1, even if you don't take another math class after this. You should say, I want to believe the fundamental theorem of calculus. In this case, this thing, our book is calling the second fundamental theorem of calculus. What about when x is bigger than 3? 8 would be more over here. It's the graph of this parabola. That parabola has a derivative equal to this line. That line is positive when x is between 3 and 5, so the graph of the parabola has to be increasing between 3 and 5, and then negative when x is bigger than 5, so the graph of the parabola has to be decreasing when x is bigger than 5. So if I try to make a somewhat decent graph here, it's a parabola, a quadratic going up and then down. Does it have another x-intercept before 8? I'm not sure. Maybe, maybe not. Let's see if, just get our technology to compute it here quick. So negative x squared over 2 plus 5x minus 8.5 equals 0 for x. 7.8 is another root of that part of the equation. So yes, it does come back to 0 before you reach 8. Something like this. Graph of capital F. We have constructed an antiderivative of little f. Let's do this on Mathematica as well. Let's do the entire problem again with Mathematica, but it'll go a lot faster. I can define a function, little f, I'll go ahead and call it u here. Little f of u by a piecewise formula. This button gives me piecewise formulas. There's 2 if u was between 0 and 3, and negative u plus 5 if u is between 5 and 8. Oops. Did I make a mistake? Oh, this should be a 3 there. There we go. So there's f of u. Could I type capital F of x is the integral from 2 to x of little f of u du? Will it give me a formula for capital F? I think it does. Okay, well, it's kind of doing it, but not as much as you might like. Okay. Let's see if it plots it, though. It might have to do a fair amount of work, but it did plot it. Okay, and yeah, that does kind of look like my drawing. Does it compute a derivative? Yes. And that is the same as the formula for little f evaluated at x. Ignore this zero true part. Okay, just look at the first two parts. Little f of x is 2 when x is between 0 and 3, and it was negative x plus 5 when x is between 3 and 8. So even though it didn't give me a formula for capital F, it did give me a formula for its derivative. Again, ignore this last part. Question? The formula for these functions is continuous. That's something I've been emphasizing, yeah. The graph of both of these functions is continuous. And moreover, this function, the capital F function, is differentiable, including where little f was not. Little f failed to be differentiable at 3, but capital F is differentiable at 3. You can see it's nice and smooth there. Oh, yeah, okay. Yep, it's differentiable. Okay. So that is the second fundamental theorem of calculus. Let's look at a statement in the book again and confirm that we are really seeing that here. The book titles the section itself the second fundamental theorem of calculus, but the theorem itself has another name. Construction theorem for antiderivatives, because that's what we're really doing. That's a more descriptive name. If little f is a continuous function on an interval, the interval in our example was 0 to 8. And if a is any number in that interval, we used a equals 2. Define a function capital F by this formula. They used t instead of u, but again, that's irrelevant. That function is an antiderivative of little f. In other words, capital F prime of x equals little f of x, no matter what x is in the interval, including if x is less than a. If a is not the left endpoint of the interval necessarily, which for our example, it was not. This theorem is always true. Okay, theorems are always true, that you can prove them to be true. When you prove them, you can call them theorems. The other fundamental theorem of calculus is a theorem as well, and therefore is always true. However, it's not always useful. The other one, back in chapter 5, little f is continuous on the interval, and if capital F is an antiderivative of little f, then you can evaluate the interval. You can find the area under the curve, or the signed area under the curve minus area above the curve when it's below the axis, by computing this difference of antiderivative values. This one is true, it's a theorem, but it's not always helpful because to use it, you have to be able to come up with a formula for capital F, which for many of our examples you can, but there's some examples like I've shown you, you can't in the usual kind of way unless you give a new name to a new kind of function, like Fresnel and ERF and stuff like that. ERF stands for error function. Let's continue illustrating these things with another example with technology to help. I like this example. Let that little f of, I'll go ahead and call it u, but it doesn't matter. Little f of u equals, say, cosine of u squared. And capital F of x be the integral of cosine of u squared. Actually, let's just do the integral symbol and then we'll write capital F's formula separately. I will start a equals 0 and go up to x. I think this is one of those Fresnel functions. Yep, Fresnel C. Not a plain Fresnel C function, whatever that is, but square root of pi over 2 times Fresnel C of square root of 2 over pi times x. It's just based on however the Fresnel function is defined. We have to look it up in the documentation center. Fresnel C. In the details, it probably has the formula. It's technically defined by that integral, which is a slightly different integral. And so the integrals are different, but they're related to each other by a change of variable, something called a substitution. I'm not going to get into details. If I let capital F equal this thing, I can differentiate capital F, and lo and behold, I get little f at x. But again, the variable name's arbitrary. I could use a xi if I want. Oh, I love that Greek letter. Xi. What's capital F prime of xi? It's cosine of xi squared. Oh, that sounded funny. Cosine of xi squared. What's capital F prime of zeta? Cosine of zeta squared. I love Greek letters. They're just so pretty. F prime of theta is cosine theta squared. Doesn't matter what the variable name is. It's the rule that matters. Can this be thought of in terms of areas? I could graph both functions here. And by the way, I also can replace in the formula for little f, even though I defined it using u, I can replace u with x. I can type this, and it's also cosine x squared. If I plot both of these functions, it's pretty interesting, actually. Oh, let's go to 3, say. Let's make the derivative be, the derivative is the little f. Let's make that be red. And the integral, antiderivative, is the capital F. Let's make that be blue. And let's think about this and see if it makes sense. So the derivative of the blue is supposed to be the red. If I think about the slopes of the blue, they're supposed to be given by the values of the red. You can see the slope of the blue stays pretty close to constant here, close to 1 in slope, just like the output of the red is close to 1 in value. Yeah, that's almost a straight line there. And if you follow that straight line forward, delta x equals 1 and delta y is approximately 1. The output of the red, the derivative, is close to 1. But then once x gets close to about 0.5, 0.6, 0.7, the blue graph slope is decreasing. The blue graph is concave down. Just like its derivative is a decreasing function, telling you slopes of tangent lines are decreasing. And the derivative is 0, horizontal tangent, when x is approximately 1.25, and that's where the red has a root. The derivative is 0 there. Then the slope becomes negative, just like the red graph has a negative output, negative value. Most negative when x is close to 1.75 or so. That's where the blue graph has an inflection point. That's where its slope is most negative. It goes from concave down to concave up then. Blue graph's concave down when the red graph is decreasing. Slopes of the blue graph are decreasing. The blue graph's concave up when the red graph's increasing. Slopes on the blue graph are increasing. Figure out the second derivative too. Make that green. Green. So the red graph is the derivative of the blue, and the green graph is the derivative of the red, which means the green graph is the second derivative of the blue.
So we just keep getting, no, we just keep getting,
The green one does at least. Yeah, it seems that way. Second derivative. Where the green graph is negative, the blue graph's concave down. Where it's positive, like in here, the blue graph's concave up. I'll get rid of the second derivative. Oops. Let's go further. Another interesting thing about this example is the oscillations get faster and faster. It's not like a regular sine or cosine wave with a fixed period, fixed frequency. The oscillations are getting faster and faster. The frequency is getting larger and larger. And the period is getting smaller and smaller. It's not a truly periodic graph. Another interesting thing to look at it with the blue graph is it seems to maybe be having a horizontal asymptote. If it does have one, it's certainly crossing it. That can happen. And if it's crossing it infinitely many times, in fact, which makes sense because these functions do involve cosine. I think this is numerical error in there. I think that's an inaccurate graph right there. If I plotted more points, it probably would fill that in better. What is that horizontal asymptote for the blue graph? I don't know for sure. I wonder if Mathematica can figure it out. What's the limit of capital F as x goes to infinity? Is it possible to figure out? It's evidently square root of pi over 2 all over 2. I didn't know that. I found out something new there today that I never knew before. Interesting. Because of the square root of pi over 2 in front, that must mean the limit of the Fresnel C function is 1/2 as x goes to infinity of this Fresnel C function, because you got the divide by 2 there. I mean, what is this limit approximately? It looks like it's close to 0.6 something. Yep, 0.626657. I have put exam questions on final exam 3 and final exams, asking you to find, for example, the first critical point of the blue graph. How would you do that? Let's do it by hand first. Almost done. Hang on a few more minutes. So the capital F function was the blue graph. It was the integral from 0 to x of cosine of u squared du. That was the little f of u. FTC part 2 says capital F prime of x equals little f of x. It's easy to find this derivative. The answer is just cosine of x squared. It's like the derivative operation and the integral operation cancel each other. In fact, this fact that I'm writing right here is equivalent to writing d dx of the integral from 0 to x of cosine of u squared du equals cosine of x squared. It's like the d dx and the integral sign are canceling. And then don't forget to change the variable to x, because that's really the true variable of this function you're differentiating. You want to make sure these three x's in those three spots match. U is irrelevant. I could call it something different. It's a dummy variable. Since that's the derivative of capital F, I can figure out the first positive value of x where it equals 0. I could also figure out other positive values of x where it equals 0. But if I solve cosine of x squared equal to 0 using the inverse cosine function, yeah, okay, its derivative is 0 right away when x is 0. No, excuse me. No, never mind. Okay. Use the inverse cosine function. X squared must be inverse cosine of 0. But that's 1. This turned out simple. X equals 1. Okay, made a mistake somewhere. Oh, what am I saying? Ah, not 1. I was confused. I was thinking cosine of 0 is 1. Inverse cosine of 0 is actually pi over 2. 90 degrees. So x must be the square root of pi over 2. Thinking too high level, making mistakes on simple things. Square root of pi over 2. Pi over 2 is about 1.57. Hit the square root, about 1.25. That's the first critical point of the blue graph, the capital F graph, when x is about 1.25. Yes, that looks about right. That's where the red graph is 0. So I have put questions like that on exam 3 before, and possibly on final exams. So it's something you should be able to do. We're using the second fundamental theorem of calculus, which is in section 6.4. By the way, we're not going to go beyond section 6.4. I might mention a little bit on Monday, but you're not going to have any homework beyond section 6.4. Okay, have a good day.